Good afternoon. In the previous class, we were discussing convolutional coding. So, in convolutional coding, there are no data bits sent at all. It is only the parity bits sent. Now, you may think if only the parity bits are sent, parity bits are less in number, data bits are large in number. So, how is it possible? But in convolutional coding, it is not happening that way. Parity bits also will not be less in number. In the sense, parity bits will be calculated here based on a particular polynomial. And then it is not like our n comma k coding, where for each number of data bits, we will have certain number of check bits. It is not that way. A complete data stream is converted into a different type of data stream using the parity bits only. So that way the stream itself is going to be sent by means of a particular algorithm. And the similar algorithm is utilized at the receiver for decoding. Let me explain without discussing further about the general methods. I have told you already about this. In applications such as wireless communication and satellite communication, the block length can run up to thousands of bits, and block length can be variable as well. So convolutional code is advantageous for such applications where block length can be variable. Now this method does not transmit the data bits, it sends only the parity bits or the check bits on the channel. But it is not just the parity bits in the sense, parity bits are generated by means of a polynomial again. So it will not be like n comma k. However, the trade-off is that the decoding process becomes slower at the receiver. At the receiver, the block decoder takes hard decisions based on the algorithms used, whereas the convolutional decoder takes soft decisions such as maximum likelihood. Now, in the case of our block coding, till now, the way in which we had discussed the encoding and decoding concepts, it was a hard decision in the sense the code vector which was received, the position of the error was detected and the error was corrected. That was hard decision. Now, in the case of a convolutional decoder, it is going to take soft decisions such as maximum likelihood. Let me not tell about that maximum likelihood now. Let me explain that later only. But the difference here is that what is hard decision, what is soft decision. Hard decision means the position of the error is known by means of the syndrome calculation and the error is corrected. That is hard decision. It's a completely mathematical approach. But in the case of a convolutional decoder, as the data bit itself is not available there, only a data stream with the parity bits are available there. Now, it has to compute on its own the data bits which are transmitted. So, in that case, it will go for a different computation at the receiver, and then it will find out whichever stream is having the minimum error. Whichever data stream which it generates at the receiver will be having a minimum error based on the parity bits that are obtained. Now, based on that, it will find out which one is most likely to be transmitted. That is called maximum likelihood algorithm. And now this is called as soft decision. Let me give a real life example. Let us say somebody sends you a letter, imagine, through the regular post, somebody sends you the letter and you only will receive the letter, you will open the letter, you will read the contents. That is called as hard decision. Okay, it is hard decision. Now instead, let us say somebody sends a message through somebody else and that message is told to you without any written document. Somebody has brought the message to from someone else. Now, the person who told you the message would not have told you everything as such. Now, based on the message which you receive, you only have to predict now about what may be the maximum likelihood message which was sent by the other person. Based on your own experience, you will have to guess sometimes, you will have to assume sometimes. Now, that is called soft decision, because you will not have the exact information which was transmitted, but you will have a general type of information. Now, you will have to guess what may be the reason for such transmission. Whereas if that person directly contacts you, or if directly writes a letter, then you can read it directly. And even then, if let us say there are some spelling mistakes in the letter, you can detect, you can correct. That is called a hard decision. But when the information coming through some other person and that person is not communicating fully, then you only have to guess things sometimes or assume things sometimes. I gave a crude example, but that is like this hard decision and soft decision. How this maximum likelihood algorithm is going to work, that I'll see later on. So the method of convolutional coding is as follows. The encoder uses a sliding window. You can see here in the diagram, you can see now there is a window here where 001 is inside the window. Now this window keeps on moving through the data stream or code vector that is being sent. Let us say this is the data stream at the transmitter. Now this window will keep on moving from left to right, and for these 3 bits which are inside the window, 2 parity bits are generated. You can see P0 of n, P1 of n. They are generated by means of an algorithm. Here an example is given: x of n XOR with x of n minus 1, XOR with x of n minus 2. That is P0 of n. P1 of n is x of n XOR with x of n minus 1. That way, for every 3 bits, 2 parity bits are generated. Now, this window will keep on moving bit by bit. And the same algorithm is applied everywhere. When the same algorithm is applied everywhere, it will take, let us say 3 bits, then next 3 bits, then next 3 bits, then next 3 bits, that way it goes on until the complete block length is completed. So here the block size can be variable. It is not fixed to n comma k type of encoding. Block size can be variable, and we can vary the block size as and when the application demands it. And for each block size, these many parity bits can be generated in this manner. Now this is called as a sliding window, which you are seeing as a rectangle on the screen. So the encoder uses a sliding window to calculate parity bits by combining the subsets of message bits. The 001 is the subset now. The size of the window in bits is called as the constraint length, denoted by capital K. Now in this example, it is 3 bits. So this is called as constraint length. Now this can also be varied based on the requirements of the application. You can see that this particular method of encoding is quite flexible, unlike the earlier methodologies. So when it is flexible, this is called as constraint length, denoted by capital K. If a convolutional code slides the window forward by 1 bit at a time and produces r parity bits per window, then its rate calculated over long messages is 1 over r. Let us say this window moves 1 bit right and again computes the parity bits. Again it moves 1 bit right and again computes the parity bits. And the number of parity bits produced here is 2. So rate is calculated over the long messages as 1 over 2. Thus the encoder looks at k bits at a time and produces r parity bits. For example, when k equals 3 and r equals 2, for every 3 message bits, 2 parity bits are generated and are transmitted. You can see here. For 001, 3 bits are there, so capital K is 3. That is the constraint length. And small r is 2. 2 parity bits are generated. And the window slides to the right side with 1 bit at a time. So then we can say the rate over the long messages is 1 over r, the data rate. So the sliding of the window is continued one bit at a time until the encoder reaches the end of the block. An example is shown below in which two parity functions are used to produce the parity bits. Now here we can represent the algorithm by means of the polynomial. We have two generator polynomials, one for P0 of n and one for P1 of n for the two parity bits or for the check bits. We have two generator polynomials. Now the coefficients of the generator polynomials are G0 equals 1, 1, 1. You can see all the three terms are present here. X of n minus 1, x of n minus 2. All three are present. So we can write the coefficients as 1, 1, 1. And for G1, it is 1, 1, 0 because in the second one, x of n minus 2 is not present. So we can substitute by 0 there. Now these are the two generator polynomials for which the coefficients are 1, 1, 1 and 1, 1, 0. Now, if the message sequence is x equals 1, 0, 1, 1, then the parity is produced using the generator polynomial as follows. If it is 1, 0, 1, 1, I will show you the complete example here. 1, 0, 1. Now, always this data stream requires 3 bits now. But the very first bit in the message sequence is 1. Now, if this is x of n, where is x of n minus 1? Where is x of n minus 2? In the beginning. So what to do? Two preceding zeros have to be assumed here, which means, let me annotate. Now we have x equals 1, 0, 1, 1, but now we require 3 bits. We have to start with the first one now. We cannot take directly 1, 0, 1. Okay. Because we have x of n minus 1, x of n minus 2. Window has to move here, right? It is the sliding window which is moving to the right side. When you start from the beginning itself, the window should have the two preceding bits, x of n minus 1 and x minus 2. So we can assume this way, 0, 0, 1, 0, 1, 1, where these two are to be assumed as the two preceding bits. Now using this, we will use P0 of 0 is 1 XOR 0 XOR 0. That is 1 because it is 1 XOR 0 XOR 0. That is 1. P1 of 0 is 1 XOR 0 because it is only x of n minus 1. So that way 1 XOR 0 is 1. So we have this answer, we have this answer now. Now the window moves next. Let us say the window moves here. Now it is 0, 1, 0. So now P0 of 1 for the sliding of the window to the right side. It is 0 XOR 1 XOR 0. That is 1. And next P1 of 1 is 0 XOR 1. That is 1. Now the window moves to the next 1, 0, 1. Now when it is 1, 0, 1, 1 XOR 0 XOR 1, that is 0. And P1 of 2 is 1 XOR 0, that is 1. Lastly, the window moves here. 0, 1, 1. So it is 1 XOR 1 XOR 0. X of n minus 1, x of n minus 2. That is 0. And lastly, 1 XOR 1. That is 0. So, we had considered the data stream as 1, 0, 1, 1. But we had assumed these two preceding zeros so as to generate check bits. Now, when we complete our check bits computation, what is the output now? Output is 1, 1, 1, 1, 0, 1, 0, 0. I am writing all the parity bits that are generated. We have two parity bits generated for every 3 bit. So this is the final answer now. This answer corresponds to this one now. Our data was 1011 and our total data stream which was going to be transmitted after computing the two parity bits each is 11110100. And you can see that data 1011 is not there here. in the stream that is going to be transmitted, the data 1011 is not there. And we cannot respectively differentiate data bit and parity bit because it's a sliding window approach. Now again you may think, for 4 bits are we sending now totally 8 bits? Yes, for 4 bits data we are sending 8 bits. Earlier also we were sending n comma k, n plus k, right? We were sending n number of message bits and k number of check bits. If it was 3 bits data, we had 4 bit parity, we used to send 7 bits. That is going to remain the same here. Only thing is, the advantage here is that data is not at all sent, only parity bits are sent, and block length is variable because block length can be hundreds of bits or thousands of bits. So, with this approach, when we complete the encoding, for the very first bit at LHS2, preceding zeros need to be assumed, as I told you. Thus, the transmitted bits are 11110100, as I had told you. You can see that result here. It can be seen that the transmitted sequence does not contain the message bits. Similarly, you can try out if x equals 101100, then the output will be 111101000110. As r equals 2 means we have 2 parity bits being generated, and as the sliding of the window is by 1 bit. Now the rate of the convolutional code is 1 by 2. As I told you, it is 1 by r. The number of bits of the sliding and the number of bits in the parity. So that way the rate of this convolutional code is 1 by 2. Now the process can be depicted by means of a block diagram as follows. You can see this block diagram now. We have this data bit coming, x of n. We need 2 flip-flops here or registers where we will have to save x of n minus 1, then x of n minus 2. So in the very beginning, these registers are reset, so we will have 0, 0. And then x of 1 is coming in the serial fashion. And P0 of n is generated by means of a 3-input XOR gate by taking all these 3 as inputs. P1 of n is generated by means of 2-input XOR gate by taking only x of n and x of n minus 1, as was the algorithm which we used which we saw in the previous example. As the preceding 2 bits need to be stored for the computation of the parity bits, we require 2 shift registers of 1 bit size, and then we require 2 XOR gates, one with 3 inputs and the other with the 2 inputs. For the previous example of 1 by 2 code, the generator polynomials were P0 of n equals x of n plus x of n minus 1 plus x of n minus 2 modulo 2 addition. Similarly, P1 of n was x of n plus x of n minus 1. So in this manner, this is the hardware which can be utilized for generating parity bits. Then as soon as 1 bit of x of n is coming, corresponding P0 of n and P1 of n will be transmitted, and the bit stream keeps on coming. It is sliding by 1 bit. Let us say for each clock pulse at the transmitter, there will be 2 bits sent out. P0 of n and P1 of n are going to be sent out. Similarly, for a 1 by 3 code, now for a 1 by 3 code, we will have to have 3 parity bits. So the generator polynomials can be in this manner. P0 of n equals x of n plus x of n minus 1 plus x of n minus 2. P1 of n is x of n plus x of n minus 1. Now P2 of n can be defined as x of n plus x of n minus 2 because that was left out. This way we can have a 1 by 3 code, 1 by 4 code, 1 by 5 code. That way we can go on. But it's of no use. When there are more number of bits, that is not of much use. So here the generator polynomial coefficients are, for the first case it is 1, 1, 1. For the second case it is 1, 1, 0. And for the third case it is 1, 0, 1. Because in the third case, x of n minus 1 is not there. So in general, the parity bit can be expressed as Pi of n equals summation of j equals 0 to k minus 1 gi of j x of n minus j in mod 2. You can see this pi of n is summation of j equals 0 to k minus 1. Now it can be gi of j, that is the coefficient. See, here you have 1, 1, 1. Here you have 1, 1, 0. Here you have 1, 0, 1. So for the three polynomials, we have three coefficient sets. That can be utilized here as gi of j modulus 2 operation with x of n minus j. In the very first case, it is g0. So x of n, g1 x of n minus 1, g2 x of n minus 2. So j is from 0 to k minus 1. Now this equation is of the form of the convolution. You have already studied convolution in the signal processing courses. Multiplication and convolution are mutual. In the sense, if in the time domain, if it is multiplication, in the frequency domain, it is convolution. If it is convolution in the time domain, it is multiplication in the frequency domain. So this term you already studied in the signal processing courses. Now, this equation is resembling convolution only. In the sense, it is a summation of the polynomial coefficient with the particular bit. When you used it with the digital signal processing, it is the summation of the coefficient along with the particular samples value, right? There also we had a digital bit stream and we had these coefficients there. Here also it is the same. It is basically the form of convolution. Therefore, these codes are called as convolutional codes. Otherwise, you may think that convolutional codes means, are we doing any frequency domain, time domain transformation here, because convolution was studied in DSP that way or signals and systems that way. It is not that way. Only thing is the expression resembles here, and the expression is that of convolutional expression. That is the reason these codes are called as convolutional codes. Now the convolutional encoder, which was shown as a block diagram in the beginning, this was the block diagram. This is the now convolutional encoder. Now a state diagram also can be written. It can be represented by means of a state diagram. You can see this state diagram. There are 4 states which are named as 0, 0, 1, 0, 1, 1, 0, 1. And there are respective outputs and there are respective bit streams. You can see, I will not go into larger detail of the state diagram because this is a representation of the particular convolutional encoder. Now, if it is 0, it will come back to the same state, or if it is 1, it will go to the next state. Same way, if it is 0, it will go to the state 0, 1. If it is 1, it will go to the state 1, 1. And in case of the state 1, 1, if it is 1, then it is coming back to the same state. That way, the same convolution encoder can be represented using state diagram. Now, why starting state is defined here? Because in the beginning, we will have to have 2 preceding zeros. And what is the advantage of representing anything in a state diagram? When we write a Verilog code or a VHDL code for the hardware, for example, now for this code, you can write a Verilog code for this hardware. For this hardware, you can write the Verilog code. In the Verilog code, you should have the Verilog code for 2 flip-flops or shift registers. Then you should have code for one 3-input XOR gate, one 2-input XOR gate. Now the bits should keep coming this way and parity bits must be generated. Now when you write the Verilog code for this hardware, you are specifically mentioning what all hardware you want. And XOR gates can be expensive. I have told you earlier also, XOR gates are the most expensive gates in the VLSI domain. Now 3-input XOR gates can be more expensive and we have 2 flip-flops. Now if you have the state diagram, now instead of writing the code for the hardware which was shown earlier, write the code for the state diagram. That's all. Now based on the state diagram, write the Verilog code for the state diagram. Now when you synthesize your Verilog code, let the Xilinx tool or the Cadence tool generate hardware on its own. In the earlier case, when you synthesize that Verilog code, it is going to generate that XOR gate only, flip-flops only, that way. But in this case, you are writing a Verilog code for the state diagram by defining the same system. All the inputs, outputs are defined here in the state diagram now. Now, based on this, we have very intelligent and efficient synthesis tools. We have Xilinx, we have Cadence, we have others also. We have Altera, if it is FPGA, or we have Mentor Graphics Synopsys, if it is full custom design, or semi-custom cell-based design, or standard cell-based design. So in such cases, let us say you write a general purpose code for the state diagram. It can be implemented on any hardware. That is one advantage. There is one more advantage. Now the resulting hardware may be smaller also compared to the previous hardware. In the resulting hardware, there may not be XOR gate at all. We don't know, because we are writing the state diagram. Based on the state diagram, we are writing the Verilog code. So the synthesis tool will generate its own logics for the hardware. It may not contain XOR gate at all. Another advantage is, when you write a code for a state diagram, that code is portable to any system, whether it is FPGA based, or whether it is standard cell based, or whether it is in any other platform also, apart from our electronics. It may be any other platform also. Now the same state diagrams code can be converted into MATLAB code, and that can be implemented in some other platform. So that way, people, when they write code for the state diagram, that becomes a highly flexible design which can be implemented, and the programs which we write through state diagram are platform independent. Where if you write through electronics hardware there using XOR gate and flip-flop or shift register, you are making it platform dependent. That is the advantage of using state diagrams. I am only revising the basics which you have already studied. So now, in general, the number of states will be equal to 2 power k minus 1, where k is the constraint length. Now the states correspond to the contents of the shift registers. The R's correspond to the parity bits that get generated for the particular input bit. You can see these arcs. For the given input bit, 2 parity bits are generated. So the R's correspond to the parity bits that get generated for the particular input bit, and the states correspond to the contents of the shift register. Each state is labeled with x of n minus 1 into x of n minus 2 up to x of n minus k plus 1, and each arc is labeled with x of n slash p0 p1. You can see this. Here the number of states is 2 power k minus 1, and the states correspond to the contents of the shift registers. We had 2 shift registers there, so we naturally have k was 3, k minus 1 was 2, 2 squared is 4. So we have 4 states here, and the states are corresponding to contents of the shift register, either 0 0, 0 1, 1 0, 1 1. Now based on the algorithm, the arcs are corresponding to the parity bits that get generated. If from the state 0 0, if the next bit is 0, parity bits are also 0 0. From the state 0 0, if the next bit is 1, then the parity bits are 1 1. This we had seen the example earlier. Now it is moving to the next state 1 0, where the contents of the shift register are 1 0. This way, you can recall the basics of your state diagrams learning, where each state can have its own label. Here the label corresponds to the contents of the shift registers. and the arcs are corresponding to input and output. Now, for the example stated above, it should be stated above, there will be 4 states and the initial state refers to the reset condition of the shift registers. That is the 0, 0. For each message bit, the state transition happens depending on the value of the input bit, and the parity bits that are on the corresponding arc are sent as shown in the diagram above. The state machine approach is highly useful for the purpose of decoding. Why? We can make it platform independent and we can optimize the hardware also, because we are giving the choice of generating the hardware not with the human beings but with the synthesis machines. You might have already studied about synthesis in the present semester as you have VLSI lab. When the digital labs start in the syllabus, you will work with synthesis tool also here. In Cadence, there is a very powerful synthesis tool called Encounter. Right now you may be working with Virtuoso in the analog designs. When we start the digital designs, you are going to start working with a tool called Encounter. That is a synthesis tool. Means you write the Verilog code that will generate the hardware. So it is the efficiency of the synthesis tool to generate an optimized hardware. That way, writing code for a state diagram or representing any system using state diagram will always be highly useful, because it can be platform independent, it can be utilized by any other designers also. Let us say I write the state diagram for this given encoder, and this can be utilized by anybody and everybody for that matter in any platform. Now let us see the process of decoding, what happens at the receiver. When the block length runs up to thousands of bits, the decoding of the same is very tedious process. As you have seen, even though we are sending the parity bits, the number of parity bits is not reduced as such. That means we are not sending a small number of bits, we are sending a large number of bits only. Now at the receiver, it is a very tedious process to decode all these big length data streams. To alleviate this issue, the convolutional decoder takes soft decisions. Let me underline it once again. It takes soft decisions in which it determines the best possible sequence of transmitter states that could have produced the parity bit sequence that was received. Which means by using these parity bits, it will not completely reconstruct the transmitted code vector. By using these parity bits, it will generate its own code vectors which are probably to be transmitted. In the sense, the receiver must have a set of code vectors which are likely to be transmitted. And out of that, which one is most likely? That is going to be utilized by the receiver. So there will be some small probability of error now. Now you can see that convolutional coding will not be as accurate as the earlier cyclic codes or block codes. There can be a small percentage of error here. But when the length of bits are quite larger, even a small error can be compromised. Sometimes the error will not be noticed at all at the receiver. For example, if I have to give a live example, using your mobile phones, you will be taking pictures. When you take pictures, depending upon the camera's resolution in your particular cell phone, you will have a picture, and that picture you will transmit or you will share it either through WhatsApp or Facebook, or you will share it in Google Photos also, or you will preserve it in Google Photos. Some of them you may make it as your profile pictures, something like that. Now you take a picture, keep on zooming. When you keep on zooming, as much as possible keep on zooming, finally you will not see the pictures. You will see only square, all squares, color squares. This you can try, or you might have already tried. You will see only color squares. But when you again zoom out of the picture, you will see that picture as it is. Which means, even though, let us say your face is present in that picture, when you completely zoom, when you expand the picture, instead of your face, you are seeing only some squares there. Each square is a pixel there. It is called as picture element. Now each pixel, if there is a small error in 1 or 2 pixels, it does not matter at all. Because when you zoom out, you are seeing your face as it is. That way, to some extent, quality can be compromised and even the error cannot be noticed at all. That is where we can take soft decisions. That means we can use convolutional coding in such applications where 100% accuracy is not expected, and sometimes 100% accuracy need not be present also in the particular application. As I told you about the photograph which you are going to click through your mobile phone, the general resolution of your camera is enough for most of the applications. Okay, but whenever a high quality application is there, for example ATM machines, in the case of ATM machines, let us say from the ATM's processor, the moment you put your card into the ATM machine till the cash comes out, there is a continuous communication there, right? Just visualize the ATM machine. The moment you insert your card is read, then on the keypad you are going to enter the amount. Whatever number you or amount you enter into the keypad, that is going to be transmitted to the CPU. There should not be any error at all. Think about that. From the keypad, when it is transmitted to the CPU, there should not be any error. But still there will be wire, right? There can be error, right? Now that error has to be detected and corrected by the CPU. Now when the CPU sends the same instruction to the vending machine to count the notes, there can be 3 or 4 trays where there will be 100 rupee notes, there will be 200 rupee notes, there will be 500 rupee notes. Now, the CPU has to decide from which tray how many notes it has to take based on the amount you enter. Now there, the CPU has to exactly communicate to the vending machine there, or the mechanism which is going to move, count the number of notes, and it is going to send it separately on a tray when it comes output from the ATM machine. There cannot be any error now. Okay. So in applications such as ATM machine, it is a hard decision. Whereas in applications such as movie projection, it can be a soft decision. Now what is happening in a movie theater? In a movie theater, basically the whole movie is digitized. It is a big file containing binary streams. Now that binary stream is going to be converted into audio and video continuously at the movie theater. Those days are gone when we used to have film roll and we used to have a projector, and then we used to have, through the projector, in front of the projector's lens, light used to be there, and this movie roll is passing slide by slide. Those days are gone. Nowadays everything is digitized. Even a movie is digitized, and projector is still there, that light is still there, but audio and video is generated by the bit streams. So in such case, in the movie theater, there need not be very hard decisions. In such a big screen, somewhere here and there, if 1 or 2 errors happen, it does not matter. Right? That is the point of taking soft decisions. I gave you all these examples only for you to understand the differentiation between hard decision and soft decision. That is where this is going to have a maximum likelihood decoder. Means, even if there are some small percentage of error, it does not matter. Otherwise, if the receiver has to again perform all the decoding operation in a different way, just like we had it in the earlier cases, it will take a lot of time. So, to reduce the time, or to reduce the decoding process's complexity. Okay, let me continue. To alleviate this issue of tedious process, a convolutional decoder takes soft decisions in which it determines the best possible sequence of transmitter states that could have produced the parity bit sequence that was received. Such decoder is called as maximum likelihood decoder. This means that from the set of possible transmitted messages, the code word with the smallest Hamming distance is the maximum likelihood one. Remember this. The smallest Hamming distance is going to be the maximum likelihood one. That means the receiver will have a set of code words and it will check the Hamming distance between the received stream and the predefined or pre-stored code word, and whichever is having the smallest Hamming distance, the receiver takes a decision that this is the maximum likelihood one which could have been transmitted at the transmitter. Let me not go into bit by bit correction, let me take it as the transmitted vector itself. Even if there is a 1 or 2 bits error, let it be there, because out of hundreds and thousands of bits, if there are 1 or 2 bits error, it doesn't matter much. That is the compromise which we do here. So when R is the received code with parity bits, C is the corresponding code word at the source, N is the length of that valid code word, and small d is the Hamming distance between C and the decoded code word. And if P is the probability of bit in the binary symmetric channel, then the conditional probability is given by this. Don't worry too much about all these things. There is a big mathematics behind this. We will not worry about the bigger mathematics here. But we are trying to define the probability. There is a conditional probability. Let me annotate. R is the received code word and C is the transmitted code word. See, R is the received code word with parity bits. C is the corresponding code word at the source. N is the length of that valid code word. D is the Hamming distance between C and the decoded code word. And if P is the probability of the bit in the BSC, binary symmetric channel, we have already seen this in the previous modules. Now the conditional probability of what? R/C. Conditional probability that for this R, C was the transmitted code word. That probability we have to find out. Now that is given by small p to the power of d into 1 minus p to the power of n minus d. D is what? Hamming distance. D is the Hamming distance. P is what? P is the probability of the bit in the binary symmetric channel. So this is the conditional probability that when C was the code word at the source, R is the received code word with the parity bits. That is capital P of R/C is given by small p to the power of d into 1 minus p to the power of capital N minus d. As I told you, we will not get into the mathematical part, but you understand this particular expression for conditional probability. I will stop here for today. Using this conditional probability, how will the receiver decode using the maximum likelihood algorithm? That one we will see in the next class, but until then you will have to remember this particular expression. We are finding out the conditional probability for the received code vector based on we presuming or assuming that C was the code word at the source. Now that will be defined by the Hamming distance. How that Hamming distance comes into picture in the decoder, let us see that in the next class. So for today I am ending the class. See you in the next class. Take care of your health. Be healthy and happy. Keep studying. See you in the next class. Bye bye.